Hi everyone. Here is the video promised for Friday. This one is going to be about going from average velocity, which we already saw, to instantaneous velocity. So for this to make sense, you should already have seen displacement, which we talked about before. Just a quick reminder, displacement. Um, it is the symbol delta x, which isn't really a new symbol in a way because x is just position, so it's a change in position. Delta x, we usually write x final minus x initial. We're still in 1D, and we said for 1D, the only thing we need here is a plus or minus sign to keep track of the fact that this is a vector. Both displacement and position are vectors and measured in meters. And in 1D, the plus or minus sign is enough to keep track of the fact that it's a vector. So we had displacement from last time, and we also have average velocity. Average velocity is a v with a bar over the top. I said sometimes in my handwriting I don't use that because I have a tendency for the bar over the top to look like the arrow for a vector. So sometimes I also will do this. Mostly for today, I think I'm going to use the bar over the top just because everything I'm doing today is either instantaneous velocity with no bar over the top or average. And then we have that as defined as in words, we could write it as displacement over time. And we just talked about what the symbol for displacement is, so we could also rewrite that delta x over delta t. I don't know if we've used the delta t for the time, but it's the same idea. So if delta x is x final minus x initial, we'd use the time. The times that match those would give a time interval. So the time final minus the time initial would be a perfectly fine way to write that. And that'll help us out today because I'm going to do some things where I talk about like x is a function of t, and it'll be really convenient to write it that way. Okay, so that's all the stuff that's gone before. And then what we're going to do today, so just to sort of give you well, it's not exactly an outline, just sort of the description of what's going to happen. Um, what we're going to do, it turns out that instantaneous velocity, I'm putting this in parentheses because after at least a couple days, we'll drop the instantaneous and it will just be velocity. The instantaneous velocity is the derivative of the position with respect to time. And we don't know how to do that yet, or at least I'm going to assume that you don't know how to do that yet, since not everybody in this class is in calculus. So I'm going to start by, what we're going to do is we're going to start with the average velocity, and we're going to let that time interval shrink. So we'll start with the average velocity, and then let the time interval shrink. So the time interval is delta t. And we'll write that in symbols by saying we're going to let delta t go to 0. Okay, so that's what we're going to do today. I'm going to start with, it's always kind of dangerous to start with a very specific case, but I'm going to start with a specific example, a special case, and talk my way through it. So back up like to the end of last time where we were doing some graphs. Example 1, which is also a special case. It's always dangerous to start with special cases, but in this case, we need to start somewhere. The special case where the velocity is constant. Constant velocity. I mentioned it in class because there was some language in one of the problems. That's also constant velocity is also sometimes called uniform motion. And that's a very special case, but it's what we're ready for. So this is a good place to talk about that. And we would have seen some examples in the last in-class worksheet when we all ended together on Wednesday. So let's say that for example 1, let's say, some object moves uniformly in such a way that it moves, I'm just going to abbreviate that, so that it moves 2 meters every second. So uniform, so it keeps doing that over and over again. So for the duration of the motion, it moves 2 meters. Every time it moves 1 second, it moves 2 meters. And so we could represent that a couple of different ways. We can represent that a couple of different ways. I guess I'll start with, let's write that as an equation. Write an equation to represent that motion. If x is in meters and t is in seconds, then we could just write x equals 2t. I need one more piece of information, which is that I should say, and it starts at x equals 0. Otherwise, if you remember the equation of a line, y equals mx plus b, otherwise I would need a constant on the end. So if I have it start at 0, then that's like a plus 0. That is a fine way to write that. You might notice, just off to the side somewhere, notice I did not feel the need to put, I'm big on units, but in the middle of an equation, I often don't. It actually does mean x is 2 meters per second times t. As long as it's in SI units, you can leave it out and not even mention it. So if it's SI units, we know, because we know t is in seconds, then we know that the 2 has to be in meters per second to get the seconds to cancel and leave meters on the left. So you could leave off the constants whenever you can figure it out by that kind of logic, which is most of the time. And there's a reason to do it later in the semester. As soon as you have the symbol m meaning mass, if you're writing units and symbols in one equation, it can be really hard to tell whether that m means meters or mass. So there's a good reason to do this, even if it seems like it's adding complication, like you have to know that that 2 is in meters per second. I mentioned you might also recognize that's the point slope form of a line, y equals mx plus b, except of course in physics I'm putting x where the y is and t where the x is, which is relevant to my next, which is to graph that. So for part B, let's just make a graph of that. You can make points if you want to. I'll graph it. I think I have some nice ways to make straight lines here. You'll just have to eyeball this. You might have lined paper, of course, so you're just going to eyeball this on your paper. I'm eyeballing it here. Oops, I want the slope to be a bit more up than that. Oops. It doesn't have to be exact because you can label the axes whatever you want to label them. So if I am saying this is like a 1, 2, 3, 4, then whatever that hits, that's got to be a 2 if this is a 1, and so on. And that's got to be a 2, that's got to be a 4, right? So I'm putting x in meters on that axis and t in seconds on that axis. I'm just really quickly, I was just making these points. X equals 2t, we can make a little table. X and t, if t is 0, x is 0. T is 1, x is 2. If t is 2, plugging into that equation, seconds and meters. 4, 3, 6, 4, 8. That's probably far enough. So, I would definitely stop and ask questions. You can pause the video if you need to think about anything. Write me a message for next time. So where I'm going with this is average velocity to instantaneous velocity. A whole lot of you might already know that for this special case of constant velocity, anytime the graph is a straight line, then any point on that line actually has the same velocity. You can do this by just eyeballing it. If you pick this interval, I'm drawing on top on purpose, or if you pick this interval or this interval or this interval, all of those intervals have the exact same rise over run, which means they have the exact same slope. So you can pick any interval on the graph of a straight line and it has to have the same slope. I'm just going to do some numerical examples. So the first question, what's the average velocity from t equals 0 seconds to t equals 4 seconds? We can use our equations, average velocity, delta x over delta t. I'm going to write it like this, x4 minus x0. As a way to keep track, I'm going to use the subscripts, just like I used them for final minus initial. Here I'm going to use them for 4 and 0. So x of 4, the equation is 2t, so it's 2 times 4. We already worked it up there. It's the same one as over there. Minus 0, anything times 0 is 0. 4 minus 0. This one's in meters, this one's in seconds. So in fact, we get 2 meters per second. 8 over 4 divides nicely, and you get 2 meters per second. I was saying any interval would be the same. I'm debating. At some point, I want to go down. I'm going to talk about shrinking the time interval, which would make it down to 0, but I don't want to always do 0 just because that's such a special case that I want you to see what I'm doing when I'm not subtracting off of 0, is what I'm saying. So what is the average velocity from t equals 1 second to t equals 3 seconds? So just a different interval there. Same thing, average velocity, only this time we take x3 minus x1 and t3 minus t1. So x of 3 seconds would be 2 times 3, and then minus 2 times 1. And I already did these, so you could look back up there and fill in the numbers from the chart too, rather than using the equation 2t. Here I'm thinking of using x equals 2t. And then on the bottom, 3 minus 1. So on the top, you get 6 minus 2 over 3 minus 1 is 2. Again, this one's in meters, this one's in seconds. So you get 4 over 2, so you get 2 meters per second. So exactly what I was saying, you pick any interval, this is the special case. For the special case of constant velocity is a straight line, not a flat line, but a straight line. In this case, it had a slope of 2. Straight line on the position versus time graph. And the instantaneous velocity is the same. It doesn't matter what the time interval is, right? So it doesn't matter how small we shrink the time interval. The instantaneous velocity is the same as the average velocity. Okay, so that's the special case. Special case constant velocity, and that should feel very familiar. I haven't done anything yet. I haven't done any calculus yet because I didn't have to, because the time interval is nothing new and different. So now let's move off of that special case. And so example 2, let's look at a quadratic in position. So let's say that an object's motion is given by motion. Do I have to write all that? Given by x equals t squared. Okay, definitely not a straight line anymore. So that's a quadratic. You could fill in a bunch of points if you want to. I'm just going to make a super quick sketch by hand. It'd be nice if I change colors. Get back to my line. So if I'm only doing half, which if I show you this does most things. So now this time if I go, that looks pretty squished. If I do my table again, if I do x equals t squared, and I have the t and the x. For 0, it's 0. For 1, it's 1, right? 1 squared is just 1. If it's 2, 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. However, far you want to go. Just graphically, so I've been talking about, I'm going to use red. So I've been talking about changing the time interval. So if I want to go from t equals 0 to whatever, that, by the way, is called the secant. So well, actually, let's just start with 5. So if I did the t equals 5 on this on that, say that spot is the t equals 5 spot. And we know that that means that if I go over, it would mean that the x equals 25. So I could use that for my first velocity calculation. So what is the average velocity from t equals 0 to t equals 5 seconds? It is the slope. Graphically, it's the slope of that secant line I just drew, right? It's the delta x, which would be the rise of that over the run of that. So it's the slope of that line. The slope of the secant line I just drew. So the line in red. So this is this pen is in red, and the line. Sorry, I'm writing so big that it's scrolling off the screen. If you're watching it on your phone, I figured it had to be this big. So what's the average velocity from t equals 0 to t equals 5? We do it the same way. Delta x over delta t, my new x sub 5 minus x sub 0, t sub 5, which is just the 5 seconds, minus t sub 0. This time is t squared, so 5 squared minus 0 squared over 5 minus 0. So 25 meters squared, right? No, that has to be meters. Yeah, 25 meters. Well, we'll have to talk about the units in a minute. There's actually no, right, there needs to be the one out front with units of meters per second squared. That's meters squared times meters per second squared. Over second squared. Oops, too many units there. 25 meters per second. Divided by 5 seconds. 25 meters divided by 5 seconds. And that is equal to 5 meters per second. Okay, so for the first interval we chose, we get a number of 5 meters per second. But if we do a different one, you can easily see that if you look back on the graph, let's see if I can find a different color. If you do another one, let's do this one in green, a very ugly green. If I pick a small value of 2.5, a little bit smaller than that would be, 2 is nice, less than half. If I do that interval, it's a pretty small interval. You can definitely see that the slope, right, which is that part, is definitely going to be less than the slope of the red line. So if we do B average velocity from t equals 0 to t equals 2 seconds, x of 2 minus x of 0, t of 2 minus t of 0, 2 squared minus 0, 2 minus 0, you get 4 meters over 2 seconds, 2 meters per second. So much, much less. So we went from a slope of 5 meters per second to a slope of 2 meters per second. So what happens is as you change this is going to be hard to show as I'm sort of drawing this. As you change the interval that you're drawing on, like a brand new shade green. So when you go from this one to this one to this one to this one. Sorry, all those should start at 0. Every time I go, that slope is going to decrease. I have a more animated way to show you this that I can show you. Maybe I'll show you when we're back in class together. So when I change that interval, when that interval gets smaller and smaller and smaller, the slope gets less and less and less if I keep the first point at 0. So if I keep the first point at 0, the slope, those of you who've taken some calculus before know that the answer of the slope of at that point at 0 is going to be, the slope is going to be 0 at that point. All right, so how do we do this algebraically? So that was me trying to show little bit of a graphical image, what it looks like. Let's talk about how to do it with algebra. So I mentioned that we're going to let this time interval shrink. So let's start with a time interval. Let's let the time interval get smaller and smaller. So I'm going to rewrite the average velocity. Well, I've been writing it as delta x over delta t. And then we've been calling it, I'll just pick x2 and x1. x2 minus x1 divided by t2 minus t1. And we've also been calling that delta x. Oh, I already wrote that, delta x over delta t. That's fine. So we're calling that delta x over delta t. We're calling that x2 minus x1 over t2 minus t1. Each of those x's I can calculate using the equation x equals t squared. The t's, so I'm saying that by pulling off that bottom row, I'm saying that delta t equals t2 minus t1. That's fine. I could rewrite that to solve for t2 equals t1 plus delta t. So I'm basically just adding the t1 onto the other side and writing it in a different order. So that when I plug it into the x, and I'm gonna do a little bit of shorthand where I'm just gonna just to drop the subscripts. I'm just gonna let t1 equals t, and this becomes t plus delta t. Just so I don't have to drag around the subscript. You'll see I'm just about to do a bunch of algebra, and I don't want to drag around. I don't want to drag around an extra subscript if I don't have to. Okay, so back to my average. So all that was off to the side. So back to my average velocity is going to be x2 is going to be the t2. I will write subscript right now. T2 squared minus t1 squared, right? Because that's the equation. X is t squared. And then divided by the t2 minus t1. T2, though, I'm going to replace this expression for the T2 so that it becomes the quantity T plus delta T squared. And then remember, I'm replacing T1 with just T. And this becomes T plus delta T. You don't really need a quantity since it's not squared down there, minus T. Here, these T's just cancel. And so that I get a nice delta T on the bottom. On the top, squaring that out, I get t squared plus 2t delta t. So the center term, or depending how you expand two terms in algebra, I do it this way, and then I get a plus delta t squared. So that's that first a plus b squared out, and then minus the leftover t squared all over delta t. Again, nicely, these t squareds cancel out. And there's actually also a delta t in both those terms that cancels. So the t squared's gone, one of the delta t's cancels, and I'm left with a 2t plus delta t. So the average velocity for any given time interval when the expression was x equals, recall, the expression was, this is only for x equals t squared. So this is also a special case, but we'll be able to generalize it when we get finished. So when you have x equals t squared as the expression for the position, and you do this trick of writing it in terms of delta t, you get that the average velocity is 2t plus delta t. That's actually true. We could work that through and see if that worked out for the expressions that we had worked out so far. But what we want to do is go to the limit. So I was saying that what we're going to do is now we're going to let that delta t go all the way to 0, and that will be the instantaneous velocity. So the instantaneous velocity is one way to write that. So that's just, that symbol is just v. And in the later chapters, it will have a vector arrow over the top. For today, I'm not using that. So it doesn't look like the average. So the instantaneous velocity, this is the way you write that, is the limit as delta t goes to 0 of the average velocity. And then you might want to write out the average velocity is the delta x over delta t to get the delta t's more explicitly in there. For this case, that means we take the limit as delta t goes to 0, and you may not know what a limit is yet, and that's okay, of this expression 2t plus delta t. And what happens when we do that is that this term just literally goes to 0. It just goes to 0. We're just going to let delta t go all the way to 0, and it's just gone. There's no delta t in this term. That term is the 2t, and even though there's a t in it, it's not a delta t. It's different, so we don't have to worry about that. So that is the velocity. So for this case, for the case where for x equals t squared, the velocity is 2t, and that is correct. So you just took your first derivative. Those of you who've never had any calculus before, you've just done a derivative. So this is even a more generic way than I was trying to get to you on the graphic, because I was only doing when t equals 0, which is a special case that you can't tell. If that's right, then you do indeed get that the velocity is 0 at that point, which is what we said earlier. But it looked like as we were drawing those secant lines on this graph, it looked like each time we drew one, the slope went lower and lower, which is what we expected. And it turns out that yes, if you go all the way to, if you use 2t at t equals 0, you do in fact get 0. I should write the derivative though for you. So the actual, if I'm going to it, and I will from now on, and I said we're going to drop this instantaneous word, velocity. Another way to write this, still the symbol v. The way to write the derivative is dx over dt. It matters that those are the cases of all of those matters. Every letter in that symbol is lowercase, and it's all the regular alphabet. And use some Greek letters at some point for different derivatives. So that's the derivative. So that says that the velocity, that equation says that the velocity is the derivative of position with respect to time. With respect to. WRT short for with respect to. So the derivative is the velocity is the derivative with respect to time. Algebraically, and if you haven't had this in calculus yet, you will, so I'm kind of jumping the gun here. It is also, another way to write that is we just were saying, it's the limit as delta t goes to 0 of your delta x, which is your average velocity. So, or the limit, if you like that better. It's nice to have it this way because there's an express delta t written in there. Whereas if you write average velocity, you have to remember that the average velocity has a delta t in it. And the other way, you also have to remember that a delta x also has a hidden delta t in it, as we solved, right? We had all those delta t's from the t plus delta t in the second term. All right, so there you go. Like I said, your very first derivative. We'll be doing more of those later. I'm going to end this video here. Well, I'll say one more thing and that'll lead into the next video. So it is not a coincidence. There's been a lot of 2s in today's video, and that's something I should have avoided. It turns out there is a general result. There's an easy shortcut that you don't have to square out that t plus delta t every single time, or cube it if you have a t cubed. Um, there's a power rule, which I could write that if x equals t to the n, so n is just some number, then it always turns out that the velocity, which is the derivative of it, it always turns out that it's n times t, and then the power comes down and gets multiplied in the front of the whole thing, and then the exponent gets reduced by 1. So when we had our x equals t squared, the n is the 2, and so it comes down, so the velocity, that's not really an equal sign, the velocity is the 2, the n, and then times the t, and then times the 2 minus 1, so 2t. So this is a way, we're going to give you basically a bunch of these rules at the beginning of the semester. Even for those of you in calculus concurrently, we'll be ahead of that class probably. And for those of you who haven't had it yet, this is the first time you've seen it. And so that's your first rule for the shortcut to derivatives. Basically, even if I had a t cubed is not that hard. You can do it. You can write that out. But once it gets higher power than that, you don't want to be squaring out all those polynomials. But you're welcome to do it to practice, to check, to see if this is true. This is just a shortcut. So this is just a shortcut of doing that t plus delta t thing, and then substituting that in everywhere there was a t in your position equation. This is a shortcut called the power rule, and we will basically give you, will basically give you a handout with a bunch of rules. There's going to be the power rule, there's going to be an addition rule, there's going to be a multiplication rule, so there's going to be a bunch of rules for how to take derivatives, and I will give you that sheet, and you will have that sheet as part of the equation sheet on the exam, so it's not something you have to memorize for this class. That's a good place to stop. I actually am going to make another. This is a good reason to have these be videos because you can go back and look at them again. I'm probably going to make another entire video about how to use this, how to use the power rule. Will be another video. So that'll be great. So and then you'll have it to look back to, which is a nice thing about having videos as opposed to class. I know it's not as nice because you don't get to ask me questions, but there are at least some advantages. All right, so I'll stop there and I'll check this video out, and as soon as it's ready, I'll post it for you. I hope I see you all soon. Bye.